All right, guys, we're going to get into chapter 16. Just up top, I want to make sure that you guys know we're going to do most of this chapter, but at the end there is pericyclic reactions. There's 3 types. We are going to cover cycloadditions, the first type. We are not going to cover electrocyclic or reactions or sigmatropic rearrangements. So if you are working ahead, you know which pieces you could skip. Okay, so getting into conjugated chemistry and pericyclic reactions, we need to talk about dienes. Now, there's no new nomenclature in this chapter because we're dealing with alkenes. You guys already know how to name those. But we're now going to talk about dienes, where we have 2 double bonds and the different kinds of chemistry that result when those double bonds are arranged in different ways. So first we have a little bit of vocab here. There's the cumulated diene. That's where you have pi bond, pi bond. Both of the double bonds share a single carbon. The conjugated systems are pi bond, single bond, pi bond. So 2 pi bonds that are separated by 1 and only 1 single bond. And then any other arrangement would be isolated, where you have double bonds, but they are separated by 2 or more single bonds. Now, this is important because we do get different chemistry, different stability and reactivity based on cumulated, conjugated, and isolated. And first off, cumulated are the highest energy. You see them the least. We're going to talk about why. Conjugated is the most stable, lowest energy. And then isolated, they have the same energy of just any other double bond. And so we're going to look at, orbitals to see if we can understand why that is. So first, when we look at the cumulated pi bonds, right, and let's just make sure we are just all on the same page, right? Your pi bonds are overlap of 2 p orbitals, right, that are parallel to one another, and the electron density is above and below that internuclear axis. Now, when you have accumulated double bond, your pi bonds are perpendicular to one another, and it forces a lot of electron density in a small area, but you don't get the kind of overlap that would kind of ease the pain. It just shoves a bunch of electron density into a small space, and so this is a much higher energy. When you have a conjugated system, they can arrange so that they're all parallel, and that actually gives you more space. You can spread out over all 3 bonds because you will get even a little bit of overlap between those 2 middle carbons. And then isolated, somewhere in the middle, it's just you have 2 bonds. They aren't hurting each other, but they aren't helping each other. So hurting, helping, they live on their own. It doesn't have to be carbon only to be considered conjugated and to have that stabilizing effect. You could have oxygen, you could have nitrogen, you could have other heteroatoms involved, and it would still be a conjugated system. Pi, single, pi, pi, single, pi. You can, anytime we learn about a functional group, you learn reactions, but you also learn how to prepare. There's nothing new here because you know how to prepare double bonds with elimination reactions. And so you're just being shown a couple different ways that you could get to butadiene, both of which taking an alkyl halide and eliminating using tert butoxide. That's one of my favorite bases right there, that bulky base. In this case, it is the Hoffman product, but it doesn't matter because you're going to make conjugated over cumulated anyway. So you could have used either base here. What's nice about tert butoxide, aside from the fact that it's a great base, is that it is not a nucleophile. So when given the choice of any base, unless I need a specific Zaitsev product, this is my guy. So you're going to see me use tert butoxide quite a bit. When we talk about just the structure, the single bond in the middle of conjugated double bonds is shorter than other carbon-carbon single bonds. And that is because both of these carbons are sp2 hybridized. And when we think about hybrid orbitals, right, just a standard s orbital is a sphere, a p orbital has that sort of figure 8 shape. And when you make a hybrid of an s and a p, it has some s character, some p character. Well, the more p's that you add, 2 and 3, the more p-like it becomes and the longer it gets. So an sp2 orbital is just shorter than an sp3 orbital because of that p character. Now, we run across these kind of graphics periodically throughout Klein. They're used to show energy, right? So what we're viewing here and what we see with a lot of double and triple bonds is we use hydrogenation reactions. So we judge the energy of the double bond compared to the energy of the resulting alkane. And when we have two isolated double bonds, we have a certain amount of energy. Here's negative 254. So when you go to hydrogenate this conjugated double bond, very similar in size, you might expect it to give off the same amount of energy. But because that conjugation is stabilizing, this whole compound is lower in energy anyway. So you get a smaller energy difference when you hydrogenate. Oh, you can tell I already worked this out. Let's erase that so we can work it out together here. Now, this is a good practice problem that forces us to combine organic 1 and organic 2. So you just learned that conjugated is the most stable, isolated is next, cumulated is the least. But you also already knew something about double bonds before you got here. You know that the more substituted, the more stable, right? You should have learned that in organic 1. That's why you make a Zate-Zeph product instead of Hoffman most of the time. It's more stable. And so we want to remember that. So I'm first going to apply the new rules that I've learned. If I'm going to go most stable to least stable, all right, this one right here, D is the most stable. So we'll say that's number 1. All 3 bonds are conjugated. Pi, single pi, single pi. In B and C, you have a pair that is conjugated and then one that is isolated. Conjugated, isolated. And then in A, you only have isolated. So we're going to say that this one's the least stable because isolated, you don't have any of that stabilizing conjugation. That's as far as this new rule can take us. B and C, you have 2 conjugated and an isolated. So we're going to go back to organic 1, and we're going to remember that we have di, tri, and tetra substitutions versus C where we have di, and tri substitutions. So B has the more substituted double bonds, so this is going to be the second most stable. And then C is going to be, is going to be third. And then, of course, our least stable we can say is fourth. All right, so that's one way to help us review a little bit of the past and practice with our present information, our new information. When we're talking about conjugated double bonds, unless they're in a ring, you're going to be able to have free rotation. Just like you could have chair flips or Newman projections, you can have anti and gauche and different staggered and eclipsed forms. You can rotate around that single bond. Now, there are going to be 2 conformations that are most stable. The cis-like or S-cis, where the double bonds are pointing towards each other, and the S-trans, where the double bonds are pointing away. These are the only 2 conformations where they're flat. So the pi bonds can all line up and overlap, and you get that stabilizing effect. S-trans is even a little bit more stable because, right, it's spreading everything out as far as possible. So you see that in this energy diagram where S-cis is a minimum, but S-trans is the global minimum. And then as it twists around, you lose that conjugation, you lose that overlap, and they become perpendicular to each other, right? And that's going to be much higher in energy. You lose any benefit of conjugation, and it's like they're isolated. Now, in this chapter, we use molecular orbital theory to explain and to analyze some bonding. Now, in my experience teaching organic and just taking organic, no matter what your experience was with molecular orbital theory in Gen Chem, no one ever seems to remember it. So I'm going to go through a little refresher here before we take a look at this molecular orbital diagram. So when you were in Gen Chem, you learned different bonding theories. You learned Vesper. You learned where you dealt with Lewis structures. You learned about geometry, right? We talked about bond angles. And then you went into valence bond. And from there, you learned about sigma and pi bonds. You learned about hybridization. Well, molecular orbital theory just continues that conversation, answers some questions that the other two don't. And it exists by now thinking of, instead of just atomic orbitals, right, those s and p and hybrid orbitals that come from each atom, well, once the atoms come together and form a compound, form a molecule, those atomic orbitals become molecular orbitals. So instead of thinking about each atom owning the orbitals and the electrons are all around those atoms, we can see how electrons could spread out over multiple atoms in a molecule. What's important to note is however many atomic orbitals you started off with the elements, that's the same number of molecular orbitals the overall molecule will have. So to discuss this, we're going to go with just the simplest bond we could possibly look at. And we're going to draw the molecular orbital diagram here in the middle, but as we are learning, as we are explaining, and we have energy up the y-axis, we're also going to draw the atomic orbitals for each hydrogen. All right, so a hydrogen atom has one electron and it's found in the 1s orbital, right? And so both hydrogen atoms would have an electron in the 1s orbitals. They should be of equal energy. And so these s orbitals, when they blend together in this new molecule, something you want to remember is that electrons can be thought of as particles, but they can also be thought of as waves, right? And when your two s orbitals come and start blending together, if they have a constructive overlap, you get a lower energy state, and we call this the bonding orbital. And in this case, it's a sigma bonding orbital. You might even see 1s written in there because it comes from 1s orbitals. Or if you get deconstructive overlap, you can get an anti-bonding orbital, and it may have the 1s, but it often will have a little asterisk by it. It's anti-bonding. So we had two s orbitals to start here. Oh, let's not underline things. And in the molecule, we have two new orbitals, one that's lower in energy, one that's higher in energy. Now let's focus on that molecular orbital diagram. Hydrogen has two electrons. We're going to fill in the diagram using the same rules that you learned in Gen Chem, right? Your off-ball principle tells you that your electrons go in the lowest energy orbitals first, and Pauli exclusion tells you that two electrons can go in the same orbital as long as they have opposite spins. And that's why you see an up and a down arrow. Now, there are no more electrons, so nothing goes in the antibonding orbital. We can really see why this bond forms, because when these two hydrogen atoms come together, the resulting orbital, where the electrons are going to live, is lower energy. And that's the really simple version. Now, what we're going to look at, we're not going to be thinking about every single orbital that is present in an atom or even in a molecule. We're going to be focusing on the pi bonds, right? And pi bonds come from two different p orbitals. Now here they're blue and red. If I draw them, I might just fill one side in. Now, if the two sides that are the same color come together, that's like the constructive overlap. They blend together and you get a bonding orbital like you see down here. If, on the other hand, you have two orbitals and they are out of phase, that's when you're going to get that deconstructive overlap. They don't blend together to make something lower energy. And if anything, it forms a node, and a node is an area where no electron density can exist. So it does not help to spread out the electrons, and so it's higher energy. We're going to be focusing more on this type of orbital. So we're going to be looking at molecular orbital diagrams that look like these guys. Now, when we think about butadiene, right, butadiene has 4 p orbitals. And so, right, as such, all 4 p orbitals were equal in energy, right? These are your atomic orbitals here. There are 4 of them, so when they blend together, we get 4 molecular orbitals. And the way they blend together give you higher or lower energy. If everything is in phase with one another, it's all constructive, right? This is going to be your lowest energy orbital. If they're in phase on each side, but not in the middle, it's still lower in energy. You do get the benefit of these two, what am I trying to say? These two positive overlaps, right? These two constructive overlaps. Now, if you have more deconstructive than constructive, like in this one, now we're in antibonding territory. These are higher in energy than the atomic orbitals if they were just by themselves. And then the highest energy of those, everything is out of phase, and you have 3 nodes. So when we think about how many electrons are present in the pi bonds, right, we want to remember that a pi bond is, a double bond is 1 pi bond and 1 sigma bond. We're not worried about the sigma bonds. We're not looking at them. We're not thinking about them. So we're interested only in the pi bonds right now. And each pi bond has 2 electrons. So if we have 2 pi bonds, we have 4 electrons that we're worried about. Now, of course, there are more electrons in the whole molecule, but we're only looking at these that came from the p orbital. So we're just looking at these 4. So we use the off-ball principle and we start here. 1, 2, 3, and 4. All of your electrons wind up in that lower energy bonding orbitals. So again, just this is more evidence of that stability. You can see how one set of electrons is actually going to be spread out over all 4 atoms, whereas the other set will be localized between, C1 and C2 or C3 and C4, but you won't find any density from that pair in between 2 and 3. You can, let's see. This is just explaining what I just said, right? You get that overlap. This gives you that a little bit of double bond character to C2 and C3, but no double bond character is found in that slightly higher energy bonding orbital. Okay. Now, you could expand on this. If you were looking at hexatriene, now we're talking about 1, 2, 3, 4, 5, 6 p orbitals. So you're going to have 6 molecular orbitals. Half bonding, half antibonding. Now you've added another set of pi electrons. You have 2, 4, 6 pi electrons to fill the chart in with. Now we get a little bit of vocabulary here. When we're talking about molecular orbitals, oftentimes comes up the idea of frontier chemistry or frontier orbital chemistry. You need to know the definition of the HOMO and LUMO. The HOMO is the highest occupied molecular orbital. Oh, nope. Let's try that again. There we go. Highest occupied molecular orbital. That is the highest energy orbital that has electrons. Here you're seeing ground state and excited state. And so in the excited state, the HOMO was different. You had an electron that was excited into a higher energy, excuse me, a higher energy orbital. Now, let me see here. Oh, and then LUMO is also really important. That's your lowest unoccupied molecular orbital. Why are these so important? Well, when a reaction happens, what electrons are going to be most likely to be involved? It's going to be those electrons that are highest in energy. If something is accepting electrons, where are they going to go? They're going to go to the lowest energy molecular orbital. So you need to know these definitions, and it is going to come up again later in our conversation about Diels-Alder.